All right, so in this class here, in this chapter, we've been talking about equilibrium expressions. We've been talking about equilibrium constants. We've been talking about the quotient, which is the mass action expression for a given equation. And now we're asked how the addition and subtraction, or addition and removal of material, or shifting in temperature or changing in pressure of reactions will alter the equilibrium of a given chemical reaction. Here we have a chemical reaction that we're told is in equilibrium, and we want to know which of the following will shift the reaction to the right. What do you think?
Let's see. Well, if you remove AgCl, that's a solid, will that shift it to the right?
I don't think that will shift it to the right. Why not? Why don't I think that?
I don't know, it's a product.
But is it in the mass action expression?
What? What does that mean?
Remember, the mass action expression for a reaction is the products raised to their coefficients over the reactants raised to the coefficients. But in this case, silver chloride is a solid, and so I don't include it in the products. I just have the silver ion raised to its coefficient and the chloride ion raised to its coefficient. So that is the quotient for this reaction. Therefore, because we remove silver chloride and it's not part of the quotient, that's not because it's a solid, that will not affect the shift of the reaction. Okay? So, how about adding HCl? What do you think that'll do?
I don't know. It's an acid, right?
Yeah, it's an acid. It's a strong acid. So when we add HCl, we actually are adding chloride ion because it's a strong acid. Good point. So what happens when you add chloride ion?
That'll shift it to the right.
That's right. Because there's more of this material, the reaction will shift to the right. Because this is in the products here. Sorry, the reactants. More of this value here will make a lower Q. And so if it's already at equilibrium, it needs to increase the Q and so shift more material to the right. So what about B?
If you add silver nitrate, that'll make silver ion.
That's right. This is a soluble compound in water. Therefore, both of these, adding these two, will shift it to the right. So we're going to say two of these will shift the reaction to the right. Okay. Now, like we mentioned, temperature also affects whether an equilibrium reaction will shift to the right or to the left. And that's because if you have an endothermic reaction or an exothermic reaction, right, then the resulting products or reactants for that reaction are as if heat. I was looking for that slide because we just wrote it not too long ago, but I can't find it. So here's an example of a chemical reaction. This one is going to be endothermic. Heat is required in this reaction, and so I write heat over here as a reactant. Therefore, if I raise the temperature, it's like adding more of this material, and it's going to shift the reaction towards the product side. All right? This reaction here is a fun one. You take some copper chloride and dissolve it into water, and if you cool it down, it becomes a blue color, but if you heat it up, it becomes a green color. And that's because the equilibrium shifts more towards one side or the other based on the temperature. So here's a reaction. It's exothermic. What will happen if the system is cooled? How will the equilibrium shift if the system is cooled?
If it's exothermic, that means heat is a product?
That's right. Heat is a product.
So if it's a product and then we are cooling it, is that like removing the heat?
That's right.
So it'll shift it to the right.
Very good. Shift it to the right. Okay. Now, catalysts lower activation energies. We talked about that last chapter. So here's an example of a reaction without a catalyst. And the purple one here is a reaction with a catalyst. The activation energy lowers. But it doesn't change, the catalysts change the activation energies, but it doesn't actually change the equilibrium. It will allow how quickly the equilibrium is reached, but it won't change the equilibrium, because lowering the activation energy increases the ease at which energy, or the ease at which molecules or reactants can form products, but it also increases the ease at which products can go back to reactants. So recognize that catalysts lower activation energy, but don't shift equilibrium. All right, so here's an equilibrium between these two solutions. Cobalt with water around it, which is blue, or cobalt with chloride on it around it, which is, this is pink, cobalt with chloride around it, which is blue. It's noted that heating this solution on the left here causes it to turn this purplish color, this blue color on the right. Is the reaction going to the right endothermic, exothermic, or we can't tell just by this much information? What do you think?
Well, let's see. So you heat it and it turns blue. So that means that you heat it and it goes to the right. Heat it and it goes to the right. That means that when you add heat, it shifts to the right. So there must have been heat in the reactant side, is that right?
Okay, very good. And if there's heat on the reactant side of a reaction, so for example, here's a chemical reaction that has heat on it, the reactant side. If I add heat to a chemical reaction that has heat on the reactant side, that would make it shift to the product side, right? What kind of a reaction would this be? Is this endothermic or exothermic?
Heat's being consumed, so it's endothermic. So an endothermic reaction is heated, it's going to go towards products.
Okay, very good. Excellent job. When all concentrations at equilibrium are known, we can use the mass action expression to find the equilibrium. All right? So, for example, here's a chemical reaction that's in equilibrium. 1 mole of this material is placed into a liter of water. If the equilibrium concentration of this material, the hydrogen ion, H3O+, and this material are both at this concentration at equilibrium, what is the value of the equilibrium constant for this reaction?
I'm not sure I understand this.
Well, can you write the mass action expression for this reaction?
Okay, I can try. Let's see, we got products. H3O+.
Very good. H3O+.
Raised to the 1. HC2O4 minus raised to the 1. Divided by H2O.
You're going to include the water?
Why not? It's a reactant, right?
It's a liquid, though.
Oh, yeah, we don't include the water. Okay, so H2C2O4.
Okay, good. So that is the mass action expression, all right? And into a liter of water, so we can draw our container to kind of visualize what's going on here, we put 1 mole of this material. It doesn't say we added anything else, just 1 mole of our H2C2O4. And then we let equilibrium be reached. And when equilibrium is reached, we find that the concentration of these products are both 0.21. And the question is, what's the K value? What's the equilibrium constant for this reaction?
Well, I don't know where to go from there. I understand, I think, what's going on. You're putting that reactant in, and you get some of the products, and you find out you got 0.21, but I don't know how you find K.
Well, K is equal to the concentration of this at equilibrium times the concentration of this at equilibrium, which we were told is 0.21, divided by the concentration of this at equilibrium.
Well, do we know the concentration of the third one? We know the concentration of the other two, I guess.
That's right. So 0.21 times 0.21 divided by, and what's the concentration of that at equilibrium?
How would we know?
Well, we put in a mole of this, and if 0.21 moles of this material results when we put 1 mole of this in, how much of this material is left over?
Oh, is that just subtraction?
Yeah, we can just take our 1 mole that we put in and subtract the 0.021, and we get not 0.021, 1 minus 0.21, so we get 0.79. All right, so this is 0.79.
Aren't you supposed to subtract 2.21s?
Now, that is a very confusing thing for a lot of us to think about. But this is like the apple, and the apple breaks down into the fruit and the seeds. So if I had one apple, and I got 1 fruit and 1 seeds, I wouldn't subtract from that 1 apple 2 things. I just get 2 products. They're different materials. So I started off with 1 molar, and then I got 0.21 of this and 0.21 of that. That means that 0.21 of this broke down. It broke down into 2 different things, but it doesn't mean that I subtract 0.21 twice. Does that make sense?
I think so.
Okay, we'll work on that as we go as well to make sure conceptually we have an understanding of what's going on. But the result is I can just take my 0.21 divided by, or times 0.21 divided by 0.79, and that value will be the equilibrium constant for this reaction. So we can identify what an equilibrium constant is by simply putting some material in, finding out how much material actually results, and we can find out what our equilibrium constant is. Okay, good job.